Good morning, everyone. Today we will continue section 3, matrix arithmetic, to discuss more operations based on the matrix. Let's review a little quick what we discussed last time. So matrix notation. We can write a matrix in this way, right? With the entry Aij. Aij means the entry in the ith row and the nth column. That is matrix notation, and usually we use capital letter A, B, C to denote the matrix. Number 2, vectors. We can write the vectors as row vector and column vector. For the row vector, we usually put an arrow, okay, above the letter. And the column vector, we just keep it, okay, we just keep the letter. Usually we use small letter, okay, small letter. So for the matrix A, we can rewrite it as n column vector or m row vectors to represent the coefficient matrix A. Next is the scalar multiplication. If we have the alpha as a scalar, alpha belongs to the real numbers, then alpha times the matrix A, that will be each entry Aij times alpha. Next one is the matrix addition. Matrix A plus B, that is at each position, at each ordered position Ij, the entry will be Aij plus Bij. And we use this capital O represent the zero matrix. Okay, so matrix A plus 0 equals 0 plus matrix A equals matrix A. Of course, this zero matrix should be the same dimension with the matrix A. And from here, we can see that the matrix addition is commutative, right? Commutative. And also, we can define the subtraction between two matrices. So matrix A minus matrix B, we can rewrite it as matrix A plus minus 1. The scalar is minus 1 times matrix B. In that way, we can define the subtraction between two matrices, right? Now, let's continue. The number 5, linear system. Okay, if we have m equations and n unknowns, then we can rewrite this linear system as in the matrix format. Okay, in the matrix format. So here, this is the standard m by n linear systems, right? Linear system. So here I can write the coefficient matrix A in this way, right? I can write A11, A12, A1n, and then A21, A22, A2n, AM1, AM2, AMN. That is coefficient matrix A. And then I can write the x as a column vector. Okay, I can write my x as a column vector x1, x2, xn. And then the right side constant b also as a column vector. Okay, as a column vector b1, b2 until bn. Okay, until bn. Then, so this is m by n matrix. This x is m by 1 row vector. This constant b is m by 1, right? Is m by 1. So we can rewrite it. We can rewrite this linear system as the matrix format. Okay, as a matrix format. Ax equals b. Okay, Ax equals b. Now let's check what does Ax mean. Okay, let's check what does Ax mean. So here, Ax, okay, AX, that will be all the equations on the left side, okay, on the left side. So my AX, the first row, my AX becomes m by 1, okay, m by 1. So how can we operate it? How can we operate it? AX, so that will be the first row. The first row is the coefficient in the first equation, A11, A12 until A1n. Then times the first column, okay, times the first column, times the column for the x. So that becomes A11x1 plus A12x2 plus A1nxn, right? Then the second row of coefficient matrix A times the column vector, okay, times the unknowns x. So that becomes the second equation because the second row shows the coefficient for the second equation. So that becomes A21x1 plus A22x2 plus A2nxn. And then the last row, AM1, the last equation, plus AM2x2 plus AMnxn, right? And then each row in AX, that is the part on the left side of the equation, then equals, so the first row equals B1, equals B2, and then the last row equals Bm. That forms the linear system. Or we can write the m by a linear system as a matrix format, AX times B, where A is the coefficient matrix, X is the m by 1 row vector because we have n unknowns, and the right side constant B is the m by 1, which means the dimension is m. It's also row vector, okay? It's also row vector. So that is the system, okay? Now, let's check this example. Write the following system of equations as a matrix equation of the form AX equals B, okay? AX equals B. Now let's figure it out. What is the matrix A, and what is the row column vector for B and the column vector for X? So coefficient matrix 3, 2, 1, 1, minus 2, 5, 2, 1, minus 3. That is the coefficient matrix for the linear system, right? And then my unknowns is all the x forms a column vector. We have 3 unknowns, right? That is the column vector. And then the right side constant B also forms a vector, column vector. And here, especially m and n, they are the same, right? It's 3 by 3. So m and n are both equal to 3. Then how can I write AX? What does AX mean? AX means the first row that gives the coefficient for x1, x2, x3, right? So that will be 3x1 plus 2x2, right? Let me write in this way, okay? Let me write in this way first. And we will discuss the multiplication later. So that is AX equals B, right? We follow that. AX equals B. So what is my AX? What is the matrix A? 3, 2, 1, 1, minus 2, 5, 2, 1, minus 3, then times the column vector xy, x2, x3 equals the right side constant B. Okay? So be careful, they are matrix and column vectors, so be careful of the format, okay, of the format. So actually the left part, this left part, A times X, we can write in this way. A times X, that is first equation 3x1 plus 2x2 plus x3. Right? That is AX. And then second equation is x1 minus 2x2 plus 5x3. The third equation is 2x1 plus x2 minus 3x3. Everyone is clear? How can we rewrite the linear system as a matrix format? AX equals B, where coefficient matrix is A with m by n format. X is m by 1, right? M by 1 column vector. Right side constant B is m by 1, right? M by 1. So that is very easy examples. So an alternative way to represent the linear system, okay, we can do like this. So we know AX, okay, AX, that is the each first, second equation until the mth equation, right? Then we can let the first column. So you can look at it. You can let it as A11, A21, AM1. They are the coefficient for the x1, right? For the first unknowns. And then the second column, A12, A22, AM2, that is the coefficient for x2. A1n, A2n, AMn, they forms the coefficient for the variable xn. So we can rewrite the x in this way, okay? We can rewrite AX. We can rewrite the equations, the m equations in this way. I can let, okay, x1, x2, xn, then that times a vector, okay? That times a column vector. So that is x1 times the first column plus x2 times second column plus the xn times the nth column. Why we need to write in this way? Okay, why we need to write in this way? Now, what does this one mean in the matrix A? This is the column vector, right? The first column vector in matrix A. This is the second column vector. This is the nth column vector. We can write the matrix A as the first column vector, second column vector, and the nth column vector in this way, right? If we use column vector to represent the matrix. So A times X can be rewrite. A times X, which is the left part, of the linear system. We can write it as the x1, x2 until xn. Each element in the x, okay, each unknowns x1, x2, xn times the column vector a1, a2, an, and then equals b, right? Equals the right side constant. Of course, equals to the column vector, okay, column vector m by 1, okay, m by 1. So this one, okay, this one actually is called a linear combination, okay, linear combination. Oh, I have to write it, okay, so let me write it. So this is a linear combination, which means the B, this column vector B can be represented as the linear combination for all the column vector A1, A2, An. Okay, everyone is clear? So here x1 each variables times the first column vector. Yes, like rewriting the linear system. Yes, x1 times the first column plus x2 times the second column plus xn times the last column, the nth column. So here, the linear system can be written as a matrix equation. Okay, can be written as a matrix equation. So we can rewrite. Okay, we can rewrite the matrix A. The matrix A is 2, 3, minus 2, right? 5, minus 4, 2, and then X. Here, matrix A is 2 by 3, which means we have 3 unknowns. We have x1, x2, x3, 3 by 1. And then the right side constant b, 5, 6, okay, 5, 6, which is 2 by 1, right? M by 1, M by 1. So here my AX, okay, my AX can be write as the matrix 2, 3, minus 2, 5, minus 4, 2 times the x. Okay, we will mention how we perform the matrix times the column vector later. Okay, when we introduce the matrix multiplication. So we can rewrite it as x1 times first column vector plus x2 times the second column vector plus x3 times the third column vector, right? So what is the first column vector? 2, 5, right? 2, 5 plus x2 times the second column vector, 3 minus 4. That is the second column vector in matrix A, right? A1, A2, A3, right? Then x3 times the third column vector, minus 2, 2. And z equals to b, right? AX equals to b. AX equals to b. So x1 times a1 plus x2 times a2 plus x3 times a3, that is b. The right side constant form as a column vector, right? That is how we rewrite the linear system. We give some simple examples. Okay, we give some simple examples. Now let's check what does this mean. Okay, what does this mean? We have x1, x2, xi. Take the sum of xi times the column vector ai. Okay, so if a1, a2, an are vectors, okay, are vectors in Rm. In Rm, they have, okay, that means each vector has m entries, right? They have m rows, okay? Each column vector, they have its m dimension, okay? They have m entries. And C1, C2, Cn are scalars, which means they are real numbers, okay? C1, C2, Cn, they are real numbers. Okay, they are real numbers. Then a sum of this form, okay, a sum of this form, which means the scalar times the scalar C1 times the column vector A1 plus scalar C2 times column vector A2 plus finally Cn, the scalar times the last column vector An. That is called a linear combination. Okay, a linear combination of the column vector A1, A2, An. Okay, linear, which means we don't have we only have the degree 1. We don't have A1 square, A2 square like that. We don't have the degree more than 1. Okay, so that is linear. So take the sum of all those, that means a combination. Okay, a combination. So that is called a linear combination. Then what does those C1, C2, and Cn means if we write AX, if we represent AX as a linear combination? So those C1, C2 until Cn, they are the solution actually, right? They are the solution for the n by n systems. So it's like if we write in this way, so that is called a linear combination, right? That is a linear combination if we can solve, if the solution C1, C2, Cn existed. If the solution C1, C2, Cn existed, which means it's equivalent as x1 equals C1, x2 equals C2, xn equals Cn, right? That means they are solutions. So if the solution existed, so the Ax can be represented as C1 times A1 plus C2 times A2. Here, C, all the Ci's, they are scalars, right? But A1, A2, An, they are column vector. Then plus xn, An equals to the column vector B, right? Sorry, here should be Cn. Cn. So which means if the n by n linear system has the solution or the solution existed, then the right side constant b can be represented as the linear combination of the column vector a1, a2 until an, right? So this is the linear combination. Linear combination of the column vector a1, a2 until an. Linear combination is a common terminology. Okay, is a common terminology when we mention the linear algebra. Okay, when we mention the linear algebra, linear model, those kind of topic or subject. Okay, so it's a common terminology. That's why we explain here. If the solution existed for the n by n system, then the right side constant b column vector can be represented as a linear combination of the column vector from the matrix A, right? From the matrix A. And actually that forms a theory, okay? Consistency theory for linear system. A linear system, Ax equals b, so we can rewrite the linear system in this way. That is more convenient to represent it in matrix notation, okay, in matrix form. A linear system Ax equals b. Here it's bolded for the letter x and b, which means they are not numbers, they are column vector, okay? They are column vector x and b. A linear system is consistent if and only if B can be written as a linear combination of the column vectors of A. That is what I said. So it can be written as x1 A1 plus C2 A2 plus Cn An equals B, right? If B can be written as a linear combination, then the solution is x1 equals C1, x2 equals C2, until xn equals Cn. That is all the scalars C1, C2 until Cn, they are solutions for the system. And this is the if and only if statement, okay? If the system is consistent, which means the solution existed, then the B, the column vector B, can be written as a linear combination. Or if we can write if and only if, that means both A and B can be the conditions, right? So If B can be written as a linear combination, then those C1, C2, Cn's, that is the solution, which means the linear system is consistent, right? We have already explained what does the statement if and only if mean last semester, right? So those two statements, right? Those two statements can be the conditions for each other. So let me just repeat a little bit. We have statement 1 and then statement 2. If we write the terminology if and only if, which means take the statement 1 as a condition, we can get the conclusion. We can get statement 2 as a conclusion. Or and not or. And if we take statement 2 as a condition, then we can conclude statement 1. That is if and only if mean. The logic of those words, if and only if. Right? So that is the theory for the consistency. Okay, consistency. Now next, we will introduce the important operation in the matrix, as well as the difficult one. Okay, difficult one. Matrix multiplication. Okay, matrix multiplication. So here, if A is M by N format, B is M by R format, then the product A times B, we can write it as the new matrix C. What is the dimension for the matrix C? So here, A is M by N. Let's figure out the format for the product matrix C. B is M by R. The product of A and B that forms a new matrix. What is this format? What is the format? So that will be A times B. Okay, be careful here. I write A times B. It's different from B times A. Okay, I write A times B. So A times B, you will notice that this is N. This is N, right? The number of the column in matrix A is N. The number of rows in matrix B, they are the same N. So the matrix, the format for matrix C will be M times R, which means the matrix C will have M rows and R columns. Everyone is clear? So that will be the number of rows in matrix A, then number of columns in matrix R. So those N disappear. The same number N disappear. The format for matrix C is M by R. Okay, M by R. And then we can write the matrix C in this format. C equals Cij, right? Matrix C equals Cij, and this small letter Cij means the entries in the ith row and the jth column, right? Then how can we get the entries for the new matrix C? How can we calculate it? Okay, how can we calculate it? So let me write the matrix A and B first. Okay, matrix A. We will use one specific example. Okay, one specific example. So matrix A can be written as the row vector. Okay, can be written as a row vector A1, A2 until AM, right? AM. Everyone is clear? Matrix A can be rewritten as a row vector, and the matrix B can be rewritten as a column vector B1, B2 until how many columns? B3, R, right? R's columns. Then what is the entry in matrix C? What is the entry Cij? What does this Cij mean? Cij is the entry in the new matrix, right? The entry in the new matrix C, or in the resulting matrix C, at ith row, right? At ij position, which means ith row, jth column. So how can I get the entry? Okay, how can I get the entry? So the entry at the ith row, jth column in the matrix C, that will be the ith row vector, times the jth column vector, okay, column vector. So for example, how can I calculate C11? So that will be the first row vector times the first column vector. Everyone is clear? Let me write in this color. Okay, let me write as a different color. So C11, the entry in the matrix C located at the first row and first column, that will be the first row vector times the first column vector, which is this one, right? And then times this one. Then what does the row vector times the column vector mean? That will be each element, okay? Each element in the vectors take the product, okay? Take the product. That's why we write k from 1 to n, aik, a1k times bk1. I will give you one specific example, then we can calculate each entries, okay? We can calculate all the entries in the new matrix C, okay? So if you realize Cij is the ith row vector times the jth column vector in B, that will be enough, okay? That will be enough. Let's check the specific examples, okay? Let me write the formula here, okay? Use a different color to represent the formula. Cij, okay? Cij will be ai row vector times bj column vector, and then that will be k from 1 to n, aik bkj, okay? Be careful of the subscript here, aik bkj. Try to take notes for the matrix multiplication, okay? In the past years, students always feel like confusing and difficult to perform the matrix calculation, okay? So first, let's check the format. For matrix A, it's 3 rows and 2 columns. Matrix B is 2 rows and 3 columns. So if we write C, okay, if we write C as A times B, what is the format? What is the format for matrix C? As I told you before, that will be the rows of matrix A times the columns of matrix B. And these two, they are same. They are n, right? They are n, then disappear. So that will be m by r, okay? M by r. This is m by n, right? This is m by n. And this is m by r. So matrix C format should be m by r. So 3 by 3, right? So for the matrix C, we can write in this way. Cij, then that equals, so it's 3 by 3, right? So we have C11, C12, C13. We need to calculate each entry, okay, one by one. C21, C22, C23, C31, C32, C33. And for the matrix multiplication, we need to calculate each entries in the matrix C. Okay, there is no shortcut. Okay, there is no shortcut. You need to calculate those 9 entries one by one. So let me give you examples. Okay, examples. So C11, let's check C11. C11, which means Ij are both 1, right? Ij are both 1. Now let me write the matrix, okay? Let me write the matrix in the row vector format. Then you will be more clear, okay? You will be more clear. So matrix A is in row vector. So that is A1, right? A1 and A2. Right? A1 and A2. So what is A1? Row vector. Row vector A1 is 3 minus 2. Right? And what is A2 row vector? Oh, sorry, we have 3. Sorry, here we have 3. Three row vectors. A1, A2, A3. So A2 is second row, 2, 4. A3 is 1 minus 3, right? And then matrix B. Matrix B is column vector, right? Column vector B1, B2, B3. Then what is B1? B1 is the first column, minus 2, 4, right? Then what is B2? B2 is the second column, 1, 1, right? 1, 1. And then B3 is the third column, 3, 6. Now, let me show you how we calculate C11, okay? C11. Let me finish. Let me give you the examples, some of them, then we can take the break. C11, according to the formula here, I and J are both 1, so that will be A1 row vector times B1 column vector, right? What does this mean? So that will be 2, 3 minus 2, then times, no need to write the cross, okay? It's a dot, times minus 2 and 4. So how can we calculate? What does this one mean? AIK times BKJ take the sum. That means 3 times minus 2. This minus 2. 3 and minus 2 plus minus 2 times 4. Here minus 2. A2, okay? A12, A11, A12, B11, B21, okay? So 3 times minus 2 plus minus 2 times 4. That is minus 14, right? Minus 14, 6 and 8. And for example, one more example, C13. What is C13? That will be A1 row vector times B3 column vector. So that will be 3 minus 2, the first row, and then the third column, 3, 6. That is 3 times 3, okay? 3 times 3 plus minus 2 times 6. So that is minus 3. So we have already calculated, okay? We have already calculated. This is minus 14. This is minus 3. So it's almost time. Let's take a break. You can think about how we calculate the other entries, okay? Then we will come back.